When we hear the word work, we usually picture effort. A farmer plowing a field, a student studying for an exam, or an artist painting a landscape. In physics, the term covers a far more precise definition. Physical actions are measured using vectors, quantities like force and displacement that possess both a specific magnitude and a fixed direction. Adding or subtracting these directional lines is straightforward. However, multiplying two vectors pointing in entirely different directions presents a mathematical dilemma. One solution is the scalar product. It strips away the directions entirely, leaving a single ordinary number, a scalar with no directional information. This raises a question. How do two directional lines result in a directionless number? And why does the physical world depend on this specific calculation? The formal geometry of the dot product is defined by this equation: the magnitude of vector A times the magnitude of vector B times the cosine of the angle theta between them. To understand that cosine, imagine a light source shining directly above vector B, casting a perpendicular shadow onto vector A. This shadow is a projection. The dot product isolates the specific component of vector B that aligns with vector A. In this sense, the dot product is a mathematical test. It measures the exact degree of geometric alignment between two forces. We can apply this logic to a measurable XYZ coordinate grid. On this grid, we use unit vectors, vectors with a magnitude of exactly 1, to define each direction in three-dimensional space. Perfectly perpendicular vectors share zero alignment. Because they point 90 degrees away from one another, their dot product collapses to zero. Parallel vectors, however, share 100% alignment. When a vector is dotted with itself, the result is exactly 1. These binary rules provide a streamlined algebraic equation. By multiplying only the components that point in the same direction, we filter out all perpendicular mismatch. Whether we use geometric shadows or algebraic grids, the scalar product serves a single purpose. It discards spatial disagreement to find pure alignment. This mathematical filtering explains why scientists rely on the scalar product to solve real-world problems. Consider a heavy object being pulled across a floor. The object moves horizontally, but the pulling force is directed diagonally upward. There is a spatial disconnect here. The force is applied at an angle, while the physical displacement is strictly horizontal. To find the actual work performed, we have to determine how much of that diagonal force actually contributes to the forward motion. Basic multiplication fails here because it cannot distinguish between useful effort and wasted diagonal energy. Physics requires a tool that isolates only the aligned force. The solution is found in the formal definition of work, the dot product of the force and displacement vectors. By projecting the diagonal force vector onto the horizontal displacement, we isolate the exact fraction of force moving the object forward. This mathematical projection effectively strips away the wasted upward energy, providing a true measure of the work achieved. If a force is applied perfectly perpendicular to the displacement, no geometric overlap exists. Despite the intense human effort, the physics work is zero. Ultimately, the scalar product is the language physics uses to translate messy, directional forces into raw, measurable energy.